All right, recording is going. So Thursday, September 2nd. You guys remember yesterday we started talking about projectile motion. So here's the agenda today. I have a warm-up projectile question, which if you paid real close attention yesterday and absorbed that information, I think you can figure this out. Okay? We're going to do a Kahoot. You guys got your phones turned on and connected. Okay? And just how the pace works out, I might have like 5 minutes at the end of class to just throw a couple other questions at you guys. Tomorrow, you guys know I'm going to pick up your guys' linear motion homework. I did want to fit in another Kahoot. Well, you guys know tomorrow is like a half-hour day. Right? So actually, the main thing I want to do tomorrow is actually have you guys do a flipbook animation. So you guys can put together all your motion information and put together something pretty cool there. Okay. So let's take a look at this. Some of you guys have been solving this. I've been doing attendance. Here's what we got. The guy got throwing a ball. Notice he's throwing it straight horizontal. Right? Throw it straight horizontal. Okay. He's standing on top of this 5-meter tall tower when he throws it, and it lands 20 meters away. Now, if you also know that he's on Earth, which is implied, then do you think that there's enough information in there that you can figure out how fast he had to throw that ball? Yeah, there's enough information lying around. Once you know that gravity's pulling down at 10 meters per second squared. You know the height of the tower and how far it lands, because he just goes out and measures that. In fact, I bet there's a way in general you can figure out, like for any tower and like any like landing distance, you can probably figure out your speed. But let's just do this with the numbers. Right, so did anybody solve this yet? Anybody know how fast he's throwing that ball? Right. So way I took you guys through some examples yesterday was I gave you guys some like check boxes. That's how we've been doing kinematic motion. Right, tax VV, those are the variables. Right, we got these 3 kinematic formulas we're juggling around, right, that tie those together. Right? But then for projectiles specifically, like this one, we're saying, well, let's separate out the vertical information from the horizontal information because those are completely separate. Right? Like how far it falls and how far it goes, well, those are motions that would be independent of each other. What's going to tie everything together is how much time. Right. See, whether you analyze this in motion from left to right, right, and wouldn't it be going across at constant speed? Like if you're up in a blimp watching this thing, guys, are there any horizontal forces pulling this ball right or left? I mean, after it's left his hand. No, gravity doesn't pull right or left, and we've been ignoring air drag, so the ball's just going to keep going constant speed to the right. Right now, that's strictly horizontally true, right? But vertically, it's a different story. Doesn't gravity pull vertically? It goes faster, faster, faster all the way down, right? Now, think about what we did yesterday. We're separating those 2 types of motion because they're each on their own axis, right? We've got horizontal axis, vertical axis, right? But whichever way you analyze it, the ball takes the same time to get to end either way, right? So, okay, just a reminder of some stuff from yesterday. Okay. Now, I'm thinking, hey, speed of the pitch, that's horizontal. He's throwing it straight horizontal, right? It goes 20 meters. I could almost want to say that this looks solvable almost in one step, because wouldn't the speed of the pitch just be like distance over time, something like that? Right? And that then would be the pitch. Speed of the pitch is, right, well, it went 20 meters. Pop that number in right there. That's 20 meters. Right? And if only I had the time, if only I knew how much time it took to traverse this 20 meters, then I could just divide those and I could immediately know how fast it was going across, right? And that would be the answer. But I don't know the time. Hey, or do you? Can you figure this out? The time that it takes to reach the bottom is constrained by what other number? About the height of that tower. Right? Doesn't make sense. The taller the tower, the more time it's going to take to reach the bottom. Ooh, right? And then for any particular speed, it would probably go further and further, right? Okay. How about this? What if at the exact same time that he's releasing this ball straight horizontally, he drops another ball? So he throws one exactly forward and he drops one. Which one's going to win the race to the bottom, race to the ground? Or do they tie? How many guys say that those 2 balls are going to tie? Yeah, okay. All the hands up. Yeah, right. Because remember that horizontal motion is independent of vertical motion. So it doesn't matter if one's going to the right really fast, right? Gravity's pulling them the same. In fact, throwing it straight horizontal, when this ball is leaving his hand, doesn't have zero velocity vertically up and down, right? Just as if they were to drop it. Right? So here's another way to frame this question to figure out how much time it takes. Right? How long does it take for anything to fall 5 meters? 5 meters. Huh. Do you guys remember this? How many seconds it takes to fall 5 meters? Who knows? Oh, yeah, Neil? Oh, I thought you were raising your hand. Right, does anybody know? Here, the answer is right on this poster right over here on the wall. Hey, look, dropping a ball off the cliff, right? For it to fall 5 meters, that took how much time? 1 second, right? Or if you want something more formulaic, we still got to figure out what is this time, right? Because no, this is all horizontal stuff. This is all horizontal. Okay. But to figure out time, we figure, okay, well, we got to go to some kind of vertical stuff. Okay. So wouldn't that be something to do with like y equals 1/2 gt squared? Okay. Well, it's really v naught t plus that, but again, whether dropping it or throwing it horizontal, v naught in the vertical direction is just 0. Okay. Okay. Hey, didn't this ball fall a total of 5 meters? Is that this guy right here? 5 meters. And it was picking up speed towards the ground at a rate of 10 meters per second per passing second. That's that. Okay. For some amount of time. It's being squared in the setup. But hey, couldn't we just do some algebra, extract this t, and then pop it in right here, and then immediately get the answer? That's what we're going to do. Right? And this is about to be a bunch of vertical information that's going to constrain the time it's in the air, therefore will allow us to solve the horizontal question that we started with. See if you guys can beat me to the answer. See if you can beat me to the answer. All right, so I'm just going to be doing my algebra. Let's see, half of 10 is 5. Right, so this would be 5 meters equals 5, and then this has units actually. It's like meters per second squared times t squared. Divide the 5 over, that's 1. Meters divided by meters per second squared becomes second squared. Take a fraction within a fraction sort of. Yeah. And then square root both sides. 1 second is equal to the fall time. Right? Yeah, 1 second. Hey, but that's what we just said. Right? Remember, we saw this backwards of what we just did in last week. If you drop a ball from the top of a cliff, how far does it fall in 1 second? 5 meters. Okay. And we just found that the other way around. So I'm going to take this number, 1 second, 1 second fall time, and say, well, it's also the time that was moving forward. That's 1 second, right? Just going to substitute that right there. Okay. Go that way. Okay. So, hey, is that 20 meters divided by 1 second? Is that 20 meters per second? Okay. That's it. That's the answer. You guys good? Okay. All right, so just to recap this, I'll explain it. Knowing the answer, right? So now you know that he threw at 20 meters per second, straight horizontal. Right? It took 1 second to fall this 5 meters because that's always true on Earth. Right? So therefore, it was flying for 1 second, and since it was going 20 meters per second, then after 1 second, it went a distance of 20 meters. Is it? Okay. All right. You guys ready for Kahoot? I'm gonna flip my screen over. Gotta present screen to share. Oh, what's that? Well, that's not what you guys want. That's what you want, right? Why is my screen so messed up? I'm so sorry, guys. I don't know why this looks like this. All right. I know you guys can't see that pen. Oh, let me try this. I'm going to flip my screen back and forth. That didn't work. Okay, hold on. Let me try this. The pin is a 4-digit number. It's 4590. Okay. The Kahoot pin is 4590. Oh, there. Okay, it's working now. My camera's not working. Yeah. Okay. I think this recorder's going to be messed up, but I'll have to deal with it, I guess. Oh no, we're back. All right. So, just in time. I think this recording is going to be salvaged. All right. So you guys are on. If you're still trying to get on, remember 4590. That'll show up at the bottom of the screen. All right. All these. We're about to do a bunch of projectile questions. These are the same questions that are on the back side of the paper with the boxes on it, right, that we were looking at yesterday. On the back side, if you want to follow along, just circle the answers just so you know what's going on. All right, and here we go. A vector is a quantity that has both what and what. Yeah, a magnitude and a direction. So the magnitude is like the number that you attach to something, and also units, right? But direction is really important for vector values also, right? So then you can say like type in tip to tail if you're adding vectors together, that sort of thing. Almost all the values we worked with in class so far have been vectors. Right? A counterexample is time. Like time is a scalar, right? So time could have a magnitude. Right? Scalars have magnitude. Right? It's like so many seconds, for example. Right? But does time have a spatial direction? No. So probably it's just a scale. But velocity, acceleration, displacement, those are all vector values. Direction is important also. Right? Matthew leading the pack. Kaylee, Bryson, Joshua, Carl. Top 5. A scalar, for example, mass, is a quantity that has only what? Yeah, only a magnitude. So there's some number you can associate with it. For example, mass could be some number of kilograms, but that has no direction. Right? Now, weight has a direction, but weight is not mass. It's two different things. Right? That's kind of a next section thing. But right. So scalars have magnitude, vectors have magnitude, and also direction. Right? Matthew and Kaylee still leading the pack. Suppose a plane can't fly 100 kilometers an hour, right, relative to the air, right, and it's getting a boost from 60 kilometer an hour tailwind. Now what is its ground speed? Yeah, because for example, if the plane is flying north 100 kilometers an hour and the wind is also blowing north at 60, couldn't you just add those? 100 plus 60 is 160, right? So after this one, I'll flip the screen and I'll give you guys notes on that one too, but just to save us the. Kaylee on fire. Math is still in the lead. Right. What is the resultant of a 3-unit vector and a 4-unit vector at right angles to each other? Right angles. What's the resultant? Ooh, all right, yeah. But you guys got 5 units, which is the right answer. All right, let me flip my screen back over. All right, back to the notes side. Right. And give you guys the notes on those last 2 questions. So you're clear on those last 2. All right. So the question before that one was like a plane flying in the same direction as the wind. So let's take a look at that one. All right. Here's the plane. Maybe the plane, its propellers can propel it forth at 100 kilometers per hour, which, by the way, is about 60 miles an hour. One comparison. But there's also a wind that's boosting it in the same direction, like a tailwind. Right? Maybe that was going like 60 kilometers per hour. Therefore, if you go from the tail of the first vector to the tip of the last one, that's what's called the resultant. Okay? And this represents the plane's ground speed, 160 kilometers per hour. Okay, so that was the last question. Okay, guys see that? Okay. That could be how fast the plane's shadow is moving across the ground, right? Or if you're standing on the ground, you have a radar gun pointed up at the plane. It's reading 160 kilometers per hour. Should use that color. Break out the darker color. Right, but the question that you guys just got was, what if the winds blow in like a crosswind? Okay. I could still make this like a plane example. Maybe this is more like a drone, and it was kind of small numbers. Okay. So what if you have a drone that can fly at like 4 meters per second? Okay, little drone can fly at 4 meters per second. Okay. Now that would be in the still air. Right? Of course, the wind can blow it around too. What if the wind is blowing 90 degrees to its motion? Right. So this drone is flying north, and we got a crosswind that's blowing east, like that. And so let's say that crosswind is 3 meters per second. Okay. Hey, isn't this the question that you guys just got? What's the resultant of a 4-unit vector and a 3-unit vector at right angles to each other? That's exactly the setup, isn't it? Right. And the resultant would be tail of the first vector to tip of the last vector. Okay. Would look like this. It's called the resultant. Okay. And that's the direction that the drone actually moves, right? Kind of northeastish. Okay. Not only is that the direction that it moves, the magnitude of this also represents the ground speed of that drone. You guys see that's a what triangle? So 3, 4, 5 right triangle. Okay. So do Pythagorean theorem. This side comes out to 5, and then the unit would be meters per second. Pythag theorem, which we've done quite a bit in this class. Okay. That's the speed of the drone's shadow across the ground. Or again, if you're standing on the ground, point a radar gun up at the drone, it's going to read 5 meters per second. Okay. You guys good? Okay. Back to Kahoot. All right. So we're doing points. Got Matthew, Kaylee, Bryson, Carlo, Israel. Top 5. A plane flying into a headwind loses ground speed. With a tailwind, it gains ground speed. What if there's a 90-degree crosswind? I just showed you guys this answer. Ooh, okay. So why would overall ground speed increase, say, its speed relative to the ground? Okay. Well, the answer is right here. It's just this. Okay. So let's go back to this drone. Right. This drone can only fly 4 meters per second. So you turn up high power, it's like, little propellers going. Right. 4 meters per second. Okay. Here's a crosswind, 90 degrees to that motion. Okay. And as a result, you get this resultant. Okay. Tail of the first to tip of the last vector. That's the direction the drone actually flies, kind of northeast. Okay. And that's its total speed, which you get from Pythagorean theorem. Okay. Yeah, it actually goes faster than it would without the crosswind, right? 5 is bigger than 4, right? You guys get that? Yeah, she takes up speed. Next question. Points. Ooh, got it. A ball is thrown into the air at some angle. At the top of the ball's path, its velocity is what? Say throw it at like a 40-degree angle or something. Oh, okay. Three of you guys got that. Entirely horizontal. Okay. Let me definitely flip the screen and show you guys why the answer, velocity at the very top would be entirely horizontal. Okay. So maybe the ground is like down here. Have a ball. Then I'm going to throw it at some angle. Okay. So let's go. It's like this. I call it like V throw. Okay. Now, if there was no gravity, it would just fly into space in a straight line forever. But there is gravity, so it's going to bend back down. Let's go with put green for this. Okay. And it's going to make the shape of a parabola, isn't it? So there's a nice parabolic path it's going to follow. Let me pick a few points and look at its motion. So maybe after 1 second, it's like here, and then after another second, it's like here, and then here, then like here. Okay, it's not exactly perfect, but we did. All right, so you guys see that when it's here, it's going to be moving kind of like this. When it's at the very top, it's moving strictly to the right. And then when it's on the way down, it's moving kind of like that. And then here, it's moving even steeper. Do it about like that. Okay. You guys see this would be its velocities, right? Its total velocities all the way across. Okay. Sure. Okay. So it's going fast, then slower, 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 and then hits the top, and then falling down, speeds up faster, 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 faster. That's why the arrows get shorter as they go up, and they get longer as they come back down. You see that? Okay. And at the top, its velocity is entirely what? Horizontal. Yeah, you guys see that? Entirely horizontal. Okay. You know what? While I've got the screen up, let me break these velocity vectors into components because I want to show you guys something really cool that hopefully you guys remember from this class. Okay. Components. So if it's going up to the right, it's going partially to the right, partially up. Okay. I'm gonna do all the right components in this light blue color. Ooh, and the top one just is that. Okay. Okay. And then I'll do vertical components in. Let me pick another color. Let's go pink for vertical. Okay. So. Okay. All right. So I just took those total speed vector, velocity vectors, and I broke them into components. Okay. You guys see the blue part? Hey, that blue part, the horizontal component velocity, is that the same all the way across? It sure is. Because there's no horizontal forces, right? So it just maintains what it's doing. So I'll go ahead and label this v sub x, and that whatever number it was starting out, it's just the same. It's uniform motion all the way across horizontally. Okay. Now the pink vector, a different story. If I take a snapshot every second, then well, here could be the numbers possibly. It might be like 20 meters per second straight up, then 10 meters per second, then 0, then 10 down. And then 20 down. You see that? Like, you see that? Okay. And of course, our approach, tell you guys since yesterday, is that if you're trying to analyze the motion of a projectile, right, you want to analyze it strictly horizontally, like the blue part, and then strictly vertically, that's like the pink part, and then you can put it together at the end. Okay. Maybe use Pythagorean theorem to get total speeds. Right? All right. So back over to Kahoot. All right, see how we're doing on points. We got Matthew still in the lead. We got Joshua moving up. Bryson, Kaylee, Carl. Top 5. A ball is thrown to the air at some angle. Let's say in the first second it moves 5 meters horizontally. How far does it move in the next second? Don't pick the yellow one. Don't pick the yellow one because that's not the answer. So in the first second it moves 5 meters. In the next second it moves how far? Who picked the other one? Yeah, you guys got that, right? So every single second it's moving another 5 meters, right? If you pick 10 meters, that would have been the total distance, but that's not really, should have left that one. Any questions about that? Because it looks like this one's moving a constant 5 meters per second to the right? Just like that, this light blue vectors that I just drawn. Joshua taking the top spot. Projectile maintains its horizontal component of speed because it is not acted on by any what? Horizontal forces, right? Because in any projectile that's just like flying through the air, right? It's only under the influence of one force, its own weight. And guys, which way does weight pull? Straight down, and that's vertical, isn't it? Right. So here, if I switch back to, okay, I think you guys really do need this visual. Okay, so let me flip back to what I was drawn. Right. So here's the projectile, whee! But there's only one force on it, its own weight, which is a gravity force that pulls straight down. It's always been pulled straight down. That's why it like bends into that upside down parabola, the arc motion, right? And that's why its vertical component of velocity is always changing. Right? In fact, it's changing at a rate of 10 meters per second per passing second, regardless of the mass of the ball. Right? You guys know that. But look at that horizontal component. And this is the question you guys just got. Right? Notice that it's the same all the way across. Why? Because there's nothing pushing or pulling horizontally. And so it's just like constant speed horizontally all the way across. Okay. You guys got that? Right. Also, what makes that true is that we've been ignoring air drag. You guys know we're ignoring air drag, right? Yeah. We'll eventually bring that back in, but not yet. Oh, Joshua on fire! Bryson, Carl, Israel, Matthew. At what part of a path does a projectile have minimum speed? Yeah, at the very top. Okay. Let you guys pick as it was thrown. Here, let me flip back to my picture and I'll show you guys exactly why the answer is at the very top. Because when you throw it, you're throwing it really fast. And it's slowing down all the way up. Is it going slower? Isn't this magnitude really big? And then it goes a little slower. And it goes a little slower. And then after that, it starts picking up speed. Then it's a little faster. And then it's but back to its original speed. Like if you threw it at however fast this is, maybe it's like 30 meters per second. Here it would also be 30. Okay. But yeah, it's slowest at the very top. Goes slower, 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 slower. And then goes faster, faster, faster. Back to computer screen. Points. Joshua still on fire. Carl moving up. Israel, Bryson, Bella. If a cannon fires a cannonball horizontally off a cliff at 30 meters per second, then how far horizontally will the cannonball move in 1 second? Yeah, 30 meters, right? Because horizontally it's been moving 30 meters per second. Okay. How far did it fall in 1 second? Careful. It picked up to 10 meters per second vertically, but it only fell 5 meters. Okay. So it fell 5 meters. It is moving 10 meters per second straight down. And then you could do Pythagorean theorem between 10 meters per second and 30 meters per second to get its total speed. But yeah, you guys are absolutely right. It moved 30 meters horizontally because it's going 30 meters per second horizontally. Yeah, all right. Joshua still on fire in the lead. It is easier to hit a home run in Denver, Colorado than in Miami, Florida. That's true. Because why? Yeah, less air drag. Okay, now it's something that we've barely talked about in here. We've been ignoring it, but we'll eventually bring it back in. That's true. Yeah, get rid of air drag. The ball will go further. So good call if you got that. Ooh, Bella on fire, moving up. Joshua still in the lead. In the absence of air resistance, what is the optimal angle to throw a ball the furthest distance? Ooh, good call. Yeah, you guys got that. All right. So let me switch my screen over. I do want to do a quick explanation of this anyway. Yeah, good call, getting that. I'm going to have you guys do a projectile lab next week. I might have you guys tackle this question or possibly a different one. Got to figure that out over the weekend. But here's the setup. Say I got a cannon. Well, there's a cannon wheel. And I can change the angle of this cannon. I could aim it straight horizontal. I could aim it straight vertical. Or I could pick any angle in the middle that I want. Right? So I can free range to whatever angle I want. Right? Okay. I'm wondering, I want to send this cannonball the furthest distance, right? Okay. just sketch this out. Now, if you aim it straight horizontal, if this cannon's right near the ground, that cannonball is not going to go very far. It just hits the ground. Okay, so if it's right after the ground, it would just be 0 mathematically. Okay? If you aim it straight up, okay, so here goes the cannonball. And it's just going to come straight back down. Get out of the way. So its displacement horizontally would just be 0. Right? You see that? Now, if you pitch it somewhere in the middle, let's say you do pick the 45-degree angle. In fact, you guys know that this is going to result in the this will be the optimal angle to the first distance. Okay. So there's like V blast, just called V. Okay. It's gonna go land there. Okay. Here's the horizontal displacement x it would have gone. Okay. And if there's a 45-degree angle that I guess should be the longest distance. Okay. See, what if you did this? There's a trade-off between hang time and horizontal component of velocity, depending on the angle of the cannon. Here's what I mean. What if you made this cannon shallower? What if you did a 30-degree angle? The 30-degree angle is right about here. Okay. Now, the cannon blast speed is still the same, but 30 degrees. Okay. Now, it might look like maybe it goes further because there's actually a greater component, horizontal component of velocity. Like, if you just look at the horizontal component, right? Actually, it's going faster to the right than at 45 degrees. But the fact that it's not angled up as much means there's less hang time. So the trade-off ends up not working out, and it's not going to land as far. It might land like right about there. What if I tip the cannon up to like 60 degrees, which is right about there? Okay. Yeah, and same blast speed. Okay. But notice what the trade-off is. Right? The fact that I'm angling it higher gives me more hang time, so it's going to be in the air for longer. Ooh, maybe that will send it further. But look at what just happened to horizontal component of velocity. See how it's not going very fast to the right? If I split this up into like a little triangle. Okay. Let's put these all up into triangles. First one was just like that, just like that. Okay, so that break out pink. Tip to tail there, tip to tail here, tip to tail here. Okay. You guys see different horizontal velocities or those fluid parts. Okay. And 60 degrees and 30 degrees do end up sending the ball to exactly the same horizontal displacement. So they'll land like both right about there. Okay. Yeah. Furthest distance, the optimal angle is 45 degrees. Good call. Back to screen. We're doing here. Okay. Whoa. Joshua, Carl, Leo, Bryson, Bella. A cannonball is launched at 30 meters per second over a flat terrain in the absence of air drag. It will land with the speed of what? Ooh, good call. All right, so notice I did not tell you what angle the cannon was aimed at, right? But that ends up being irrelevant information anyway, right? Because symmetry. Right? You guys remember this from a few minutes ago? Whatever the blast speed is, it's going to go slower on the way up, it's going to speed up on the way down, and for equal elevations, it's equal speeds. Okay? You guys remember that? All right, see how we're doing on Kahoot. Got Josh keeping the lead. Carl in second, Bryson's moving up. A projectile is launched horizontally, hits the ground in 1 second. Ooh, sounds like your starter question. If it had been launched at a faster speed, and horizontally, what would happen to the hang time? Say the same. Okay. Let's read that question really careful. A projectile is launched horizontally. You guys see that word horizontally? Now that's key. So it hits the ground in 1 second. What if you had launched it faster instead? Okay. I want to refer back to you guys' starter question. You guys remember? You guys remember this question right here? And this was the full solution, right? So this guy's throwing some ball horizontally. Okay. The fact that it fell 5 meters, you guys remember that did take 1 second? That could also pertain to that Kahoot question. So actually, you also know you're on top of a 5 meter tall tower in that Kahoot question, don't you? Just fall in 1 second. 5 meters. You guys know that? Okay. Right. Remember I asked you guys, what if this guy drops the ball at the same time that he throws it? Which one hits the ground first? And you guys said what? They tie, right? What if he throws it twice as fast? They're still going to tie? Right? So whether he drops it or kind of lobs it slowly or throws it like, right? Wouldn't all these reach the ground at the same time? Right? They do, right? As long as it's not so fast that it overcomes the curvature of the Earth, which we've not run into yet. So, yep, they're all going to tie. Same, here you go. All same. Okay. Who's got any questions so far? Any questions? Okay. All right. Oh, an object is thrown horizontally at 30 meters per second from the top of a cliff. What is the acceleration as it's in free fall? Oh yeah, 10 meters per second squared downward. Remember, anything in free fall is always accelerating toward the Earth at 10 meters per second squared. Okay. So that's the only way it's being pulled. Oh, Josh is on fire. Carl, Bryce, and Neil, Bella, up in the top 5. Neglecting air drag, at what point is acceleration greatest for a ball thrown straight up vertically? Yeah, isn't it the same everywhere? Right? Because if you throw a ball straight up, as soon as it leaves your hand, isn't it accelerating down at 10 meters per second squared? What about when it's like halfway to the top, still accelerating down? What about at the very top? Is it still down 10 meters per second squared? Yep. And then when it's falling back down, right? The entire time it's in free fall. It's always down 10 meters per second squared. Yeah. You guys get that? Yeah. That's the acceleration. Ooh. Yeah. So jockey in for a second. Suppose you can jump 1 meter vertically. That's a pretty good jump. If you were on a skateboard that's moving to the side at 15 meters per second, now you can jump how high? Yeah, look at you guys, right? Because you guys know that vertical information and horizontal information, those motions are independent of each other. So it doesn't matter if you move into the right really fast, you can still jump the same height. There you go. Okay. This is new stuff. I want to see if you guys can figure this out. When in orbit, a satellite such as the space shuttle. Ooh, okay. Glad you guys got that. If you did, then definitely awesome because I have not told you guys this yet. So let me flip back over to the screen and show you guys why that's the answer. All right. So usually what we've done so far with projectiles and what's going to be true on the quiz is we're basically assuming a flat Earth, which is approximately true locally. Okay. But if you get big enough, okay, like you got the whole Earth going on here, get the equator and a pole going. Like this International Space Station flying around, okay, that's actually approximately where it is proportional to the size of the Earth. Right? Like here's the radius of the Earth. Call that radius of Earth. Right? The elevation of International Space Station is only a few hundred kilometers up. In the big scheme of things, it's not really that far up. This path might do something kind of like this. It goes behind the Earth. Okay. In fact, if you build a 400-kilometer tall tower, I think I asked guys this like second day class. At the top of the tower, you feel like you have about 90% of your weight. It really isn't a whole lot different from the actual surface. Right? But International Space Station flies by, everybody looks weightless. How's that? That's because they're flying so fast that by the time they move to the side, they've gone so far around the curvature of the Earth. In 1 second, they'll fall 5 meters, but the curvature of the Earth also changes by 5 meters, so they don't actually get any closer to the surface of the Earth, right? That's why they feel weightless. They feel the same way you would feel if you jump off a building, right? You'd feel weightless. Okay? But there's still a gravity pull on them that's almost their surface weight. They're still accelerating because they're moving in a circle. Their direction of motion is changing. Right? We'll eventually get into circular motion, so that'll come back. But yeah, awesome if you figure that out. All right. Preston's on fire. Joshua's still holding the lead. A ball is thrown straight up at 20 meters per second. It will return to the ground with the speed of. Yep, 20 meters per second. Right. Real fast. Show you guys that I did sort of give you this answer already. Right. You guys remember this projectile? Right. No, it did say straight up. So if you just focus on the pink part, there could be a ball side by side. Just goes with it. 20, 10, 0, 10, 20. Symmetry. All right. One more Kahoot question. Here's the last one. This is for the medals. Ooh, Josh is on fire. A cannon with a barrel velocity of 120 meters per second launches the ball horizontally from the top of a cliff. How far will the ball fall in 3 seconds? How far does it fall in 3 seconds? Oh, only 3 of you guys got that. Okay, so I'll draw this out in a minute, but for now, let's use our imaginations. Can you guys imagine a cannon perched at the edge of a cliff, and it's aimed straight horizontal, right? It blasts out a cannonball 120 meters per second, the ball's like flying off the edge of the cliff, right? But it's aimed straight horizontal, right? So wouldn't the vertical motion be as if you just like dropped the cannonball off the edge, fly side by side, right? So the question, how far does the ball fall in 3 seconds? Well, isn't the answer to that the same as, you guys see this poster over here on the wall? Just dropping a ball off the edge of a cliff? How far does anything fall in 3 seconds? Something like that. About 45 meters, right? As long as you're on Earth. Okay. Hey, that's the college equation. That's like Paul Hewitt mineshaft, except it's only 3 seconds instead of 5, right? Remember if it was 5 seconds, it'd be about 125 meters. This is 3 seconds. Right. Draw this out. Draw this out. Right. So we got cliff, cannon, horizontal blast, 120 meters per second. Okay. 1 second later, it might be about here. Then 1 second after that, maybe about here. 1 second after that, maybe about here. Okay. It's always going 120 meters per second to the right. That didn't change, but that wasn't the question either. Okay. It's always 120 meters per second to the right. Okay. The question was, how far did it fall? You guys remember, after the first second, it falls 5 meters. Then after the second second, it's fallen a total distance of, 20. There you go. 20 meters up to here. Okay. And after the third second, now we're down to 45 meters. Okay. Where'd that come from? That comes from how far it falls. I'll call it y equals 1/2 gt squared. Okay, you guys remember this? Okay. So if you plug in 10 meters per second squared, 1/2. If you do that for 3 seconds, and square that number, because times 0, 1, 2, 3. Right. Okay. Notice, hey, take a look at this nice parabola. You guys see that nice parabolic path right there? Okay. 3 squared is 9 times 10 divided by 2. This comes out to be 45 meters. That's where I got this number right here. It's fallen. And again, if you drop the cannonball at the same time, it also would have fallen. Here's time 0, time 1, time 2, time 3. See how it's like spreading out? Right? In 3 seconds, it's going to fall 45 meters. Same thing for anything shot horizontally. Okay? You guys get that? Okay. We have time for one more thing. That's to find out who won these Kahoot medals. With the bronze, Carl. Who got the silver? Bryson. And the gold, Joshua. All right, nice. Confetti dance. Oh, we got some runners up. Got Bella and Neil. All right. Yeah, nice job, guys. All right. Who's got any questions, anything today? All right. Well, that is a wrap on class because bell rings in a few seconds.